Uh, well, on behalf of the Atal Academy, the MS Institute of Technology, and on behalf of all the participants, I extend a very hearty welcome to Dr. Anandh Subramanian. We thank him for having accepted our invitation to speak to this, during this faculty development program. There are faculties from mechanical department, even from chemistry department, materials department, from across the country, from all over the country. We have people, and we had a very lively sessions in the morning, and there were quite a lot of questions, Dr. Subramaniam, in the morning. So I guess you may have to get ready to answer quite a few questions this afternoon. So for the sake of participants, I have the pleasure of introducing Dr. Subramaniam. So he has given me a brief CV, so I don't have to, make it short myself. He's given a very short CV of himself. Let me read it out for the benefit of the participants. Dr. Anandh Subramanian did his BTech from IIT Madras, followed by a ME and PhD from Indian Institute of Science, Bangalore. Then he was a scientist in CSIR, followed by the position of a guest scientist at Max Planck Institute for Metals Research at Stuttgart as a Max Planck Fellow and as an Alexander von Humboldt Fellow. After being a faculty in the Department of Applied Mechanics in IIT Delhi, he joined IIT Kanpur in the Department of Material Science and Engineering. Selected awards received by him include the Sriram Arora International Award for Material Science and Engineering Education, given by TMS USA, and Young Researcher Award, given by IUMRS. His areas of interest are physical material science, nanomaterials, quasi-crystals, amorphous materials, metastable materials, epitaxial systems, defects and interfaces in materials, symmetry, crystallography, and hydrogen storage in materials. The primary tools of research are transmission electron microscopy and finite element method. Using theory, computational theory, computer simulation, and experiments, Dr. Subramanian has published papers on metals, semiconductors, and insulators. He has prepared 2 video courses, and his ebook called Material Science and Engineering, a Learner's Guide, is referred to globally by students and teachers. He has executed multiple projects ranging in topics from transmission electron microscopy to FEM. He has recently established the IIT Kanpur wing of the Multi-Institutional Center on Hydrogen Energy Systems under the aegis of the DST, Energy Storage Platform on Hydrogen, which is located in the Center for Environmental Science and Engineering at IIT Kanpur. He is one of the founding members of the Department of Sustainable Energy Engineering at IIT Kanpur, which has hydrogen energy as an important focus area. That's Dr. Subramanian for you. Sir, the screen is yours. We look forward to your thing. Generally, it's about 1.5 hours of presentation, and last half an hour is for discussion. My suggestion for all the participants, asking questions orally at the end takes up a lot of time. When you have a question, please chat, type it down on the chat. Maybe in the same order, Dr. Subramanian will answer at the end. Thank you, Dr. Subramanian. Please take over.
First of all, let me thank Professor Fanish for his kind invitation, also for the Ramaya Institute of Technology. Though it was next door for many, many years, I have not visited. I think only once I have come there. So maybe in the future, I will try to visit and also meet Mr. Fanish.
Yes, please.
He was talking about this sustainable energy engineering. So Professor Shobhit Tomar, who is also speaking in this conference, is also like me in both material science and engineering and sustainable energy engineering. I hope my voice is coming loud and clear, right? There is no problem with my voice, right? And my video is also reasonably clear, I hope.
Absolutely, both are fine. Go ahead, Doctor.
So I thank all of you for being present here today. For many years, I asked myself this question: what can you gain from a small QIP seminar? Okay. So one thing is clear, that you cannot understand everything which is being told. If you try to understand everything, for instance, nanomaterials and nanostructures range from mechanical applications to electrical applications to all kind of applications, bio applications. And therefore, the fundamentals of these subjects, if you do not have a fundamental, suppose I don't understand, personally, I don't understand mechanics very well. then obviously nanomechanics will be a big challenge for me to understand, right? So if I don't understand band structure of metals and I try to understand band structure of nanomaterials, that may not be possible. And therefore, people who approach nanomaterials, they typically come from either one of the fundamental areas of chemistry or physics or materials, like they could be from magnetism, they could be from mechanical behavior. Uh, so, therefore, do not try to understand everything I say today. The slides will go a little fast. Uh, the idea of such a TechWeb talk or a QAP talk or an ATL talk, to my best of my understanding, is what is called you get try to gather an exposure. Okay? And also the second thing you come to know is that who are the people you need to be in touch. Like typically, I have questions say about entropy. I approach people like Srihari, who is in chemistry. I have other kind of questions on magnetism. I approach, say, Somin Mukhopadhyay or one of those people. So you need to know the people who are working in this area, and such a platform usually gives you a feeling that who are the people, where are the facilities in the country tomorrow if you want to pursue research or you want to, uh, use some of the facilities, where are they located? So that is, should be the primary goal. It will be, if not difficult, impossible for you to understand whatever I'm going to be saying today. However, I hope I can give you a reasonable exposure to the various aspects of nanomaterials and nanostructures. I hope also I can give you a certain flavor of how such materials can be fascinating. Okay. The goal today will also be to warn you that there is no magical potion called nanomaterials. It's not like you get into nanomaterials and then you're going to get all fantastic things happening. You have to be a little careful. Um, but then there are a lot of exciting things which can happen when you do study nanomaterials. The typical um, references I've listed here, the Encyclopedia of Nanoscience and Nanotechnology is an extensive book. It's a huge multi-volume book, but that's a comprehensive volume. You may refer to it. Nanomaterials, Nanotechnologies and Design by Ashby and co-workers is a very good resource. If you want briefly to understand the subject, it's a very good resource. Um, the ebook, right, which I'm pointing to the left-hand side, that ebook is gives you fundamentals of material science and engineering. It's not specifically tailored for nanomaterials, but it covers the fundamentals of material science and engineering, which ranges from phase diagrams to thermodynamics to mechanical behavior. Now, on the right-hand side is the NPTEL lecture, and this is specifically tailored for nanomaterials. So this NPTEL lecture could be a little slower. You may want to go through these NPTEL lectures to gather some more knowledge, which I will be briefly touching here today. Let me start with the nanoscale. Okay, this is the easiest part of the whole talk, which is the nanoscale. Where does it lie? On one hand, you have components. The components could be a gear wheel. It could be a device in your computer, like a computer chip. And on the other end of the spectrum are atoms and unit cells. Now, if you want at the level of the unit cell, the next level is where the crystalline defects reside, and this is of the order of nanometers. Okay. Then you have the next level, which is called the scale of the microstructure, and we will talk a little bit more about this. What is this microstructure? So, somewhere in the range of multiple unit cells and where the dislocation stress fields lie is your nanoscale. That means that's the scale we are going to focus today, and definitely larger than the scale of the atom. Okay, so we are going to be somewhere between the hydrogen atom and the blood cell as shown in the diagram below. But we will also, I'll also warn you that just because something is in the nanoscale, it does not mean that you're going to get interesting properties. Something may be in the nanoscale and yet nothing interesting may happen. So please remember this. And therefore, and also that just because you're in the nanoscale, it does not mean as a function of time, the structure would be retained in the nanoscale. So please remember this. Let me start with a gallery of a few pictures for you. And this gallery will tell you that what kind of nanostructures are possible. Then this is a nice, what you might call the photo gallery. Later on, we will take up individual cases. Most of the pictures I will be showing you are either generated in the lab or some neighboring lab, except for a few, like for instance, the nanotube, which I have shown on the right top, is taken from the net. But most of the others are actually taken either in our lab or some lab in IIT Kanpur. Okay. So you have nanostructures, and we will define nanostructures very soon, like freestanding fullerene molecules. It could be the domain wall in a ferromagnet. It could be silica nanoparticles. Okay. these are amorphous. It could be the grain boundary region in a silicon nitride ceramic. And these structures, which you see here in the bayonet, also some of them are in the micron scale or sub-micron scale. Carbon nanotubes are in the nanoscale regime, and you could have single-wall nanotubes or multi-wall nanotubes. So these are nanostructures. Okay. Next, we'll see some nanocrystals. And the nanocrystals you see on the left is, I think, a palladium nanoparticle, which is, you can see here. Then you have a hollow structures. So this is a hollow single crystal, which is again in the nanoscale. It's about 100 nanometers. You can see the scale bar here. And how do you know it is single crystal? When you take a selected area diffraction pattern, you see that it is a hollow but single crystal. Then you see nanocrystals of gold here on the left-hand side. So you can see these nanocrystals have faceted surfaces. And then there are small nanocrystals of lanthanum LaNa5, which are embedded in a magnesium matrix. So this is some kind of a two-phase mixture you're seeing, or a three-phase mixture, in which you're able to see NaNa5 crystals. So these are nanocrystals. You can have nano hybrids. We'll soon see what are hybrids. They are a super class of composites. And in the middle, you see a nickel and carbon nanocomposite. The yellow dots, this is an EDX map, energy dispersive X-ray map in a scanning electron microscope. The yellow dots are nickel nanoparticles, which is embedded in a matrix of carbon. On the left-hand side, you see a nano capsule. That means there is a nickel capsule inside which there are hollow structures of magnesium. So there is a double level capsule, outer hollow structure and an inner hollow structure. And the inner hollow structure is magnesium, outer is nickel. On the right-hand side, you see a multi-layered structure, like a sandwich structure. And here you have silicon, germanium, and GD2O3. So this is also a nanostructure. This picture on the right-hand top was given by Professor Somnath Bhattacharya, who was originally at TIFR and now at IIT Madras. The bottom picture is from Kantesh Balani's group, in which they have made a composite of carbon nanotubes, and this is alumina matrix. So why are they doing this will be clear, but this is an example of a nano hybrid. On the left-hand side is an interesting kind of a hybrid in which you have the, what you might call pores, and this is porous alumina. So they grow this porous alumina structure on aluminium using sometime electrolysis methods. So these are all examples of nano hybrids. If you look at nano, then the question comes, what else can be nano? Virtually, you can see the word nano is extended today to every single thing, like from nanomechanics to nano indentation. You see here nano indentation. In nano indentations, the depth of the indentation is nanoscale. You can have nano surface steps, as shown on the bottom left. You can even have nano explosions. So the way we created these nano explosions, we had oxygen-filled palladium hollow spheres, and then we had hydrogen-filled palladium hollow spheres, and we mixed them together, and you can see the explosion has broken these spheres. So virtually anything can be called nano, and this is the what you call the enrichment which has happened in about last 15 years or so in the field. There are also nano devices, and when you say a nano device, the whole device is not nano, but there are certain features in the device which are at a nanoscale. For instance, you can have a super lattice where you can see the multi-layered structure in which there is a super lattice of aluminum gallium nitride on gallium nitride, and typically these are epitaxial super lattices, and you would find that this layer thickness is in the nanoscale. So this is all, and some of these properties you see here comes from the fact that you have kept this in the nanoscale. One of those properties is something called the formation of a 2D electron gas in such kind of devices. The figure on the right-hand side is a simulation of the stress state of such a system, and you can see that there is compressive and tensile regions. So in epitaxial islands also, for instance, one of the experts in this area is Professor Madhav Ranganathan in chemistry department here, who does kinetic Monte Carlo simulations to grow these. You have epitaxial islands, which are also can be in the nanoscale. Not only can you have individual structures, you can have something called hierarchical construction of these structures. And one nice example we'll take up again is called the Abalone Shell. This is a living organism, and it's a shell of that. And you have a two-layer structure initially. You zoom in a little bit, you see that this is made up of brick kind of structures. these individual bricks are extremely brittle, but then the overall composite is highly tough and its impact resistance. This organism wants to live, and therefore when it's thrown against the rock or something, it doesn't break easily. So you have these very thin structures. And these pictures again were taken in the lab by one of the students who actually bought this Abalone Shell from the market and made this beautiful micrography. And this is even better than what's found in textbooks. And the other hierarchical structure, which is the Lotus Leaf, and it has a property. So what is the property of this Abalone Shell? It has got impact toughness, though it is made of brittle layers. What is the property of this Lotus Leaf? It is what is called super hydrophobic. That means if water falls on the Lotus Leaf, it sort of slides over. And it's a hierarchical structure consisting of these protrusions inside a base, and on the protrusions and the base there are nano hairs. And this overall hierarchical structure is what which endows this Lotus Leaf with the super hydrophobicity. Okay, that means it repels water. Nowadays people have made tanks, etc., mimicking these kind of structures, and therefore when you pour out liquid from that tank or a container, it completely cleans itself out. So you don't have to clean the container after emptying it. Now, what is that we are interested in? We want to have some interesting properties and an interesting performance in perhaps a device. And that means that I need to know what kind of properties they exist. Okay. So there are two kinds of properties, as we shall see in the next slide, what are called the structure sensitive properties and the structure insensitive properties. So when you say structure, the word usually implies microstructure, and yield, stress, fracture toughness, etc., when you do a tensile test, are called structure sensitive properties, while density and elastic modulus are considered structure insensitive. And today we will see that even the so-called structure insensitive properties like elastic modulus or density can change in nanomaterials, and the change can be significant. Now, what determines the properties of materials? Suppose you take your conducting wire, which is copper. If you have a few tens of parts per million of oxygen in it, it can actually degrade the conductivity of oxygen, the copper wire. That means composition can be a very sensitive function. It also can be how the phases are distributed. Suppose you have cementite along the grain boundaries, and this is steel with what is called an hypereutectoid steel, then this crack can propagate all along the brittle cementite, and therefore you can have an intergranular fracture. Intergranular fracture, and the material maybe have very poor impact toughness. It may also depend on the defect structure in the material, as you can see below. That means if you remove all the dislocations from a crystal, then the crystal will attain strength of the order of gigapascals. While actual yield strength of materials, of the order of 100 megapascals or so. That means that the crystal is weakened by one or more orders of magnitude, and this happens because of the defects. And it depends on how these defects are distributed. Last but not the least, the properties also depend on what is called residual stress and the distribution of that. Now, you may think that, residual stress is something which is intangible, and how can it affect the properties? It can have profound effects. For instance, in Kanpur, there are 3 ordnance factories. One of them make these gun barrels. The T90 tank gun barrels are made here in Kanpur, where I sit now. And they warp because of residual stresses. When they manufacture these and do the heat treatment, they warp. The whole barrel bends, and they have to spend a lot of effort straightening it. So this is a negative effect of residual stress. On the other hand, if you look at toughened glass, there is toughened glass. Asahi and Saint-Gobain, etc. manufacture toughened glass. And the toughness of these toughened glass comes from residual compressive stress on the surface. So residual stress can be positive or negative. And if you look at these epitaxial islands, if you put and typically these epitaxial islands could be silicon germanium on silicon substrate. You put a capping layer and then grow a second layer, then you will find there is a strain alignment. That is, when the second layer of those epitaxial islands may be growing exactly over the first layer, though they may not directly see them. So what does the properties depend on? It depends on composition, phases and their distribution, the defect structure and residual stress. And you can have combination of these aspects determining the properties. So we have introduced a term called microstructure, because this is the next level of structure after these nanoscale, right? It's a microstructure. But suppose I'm looking at in a transmission electron microscope, and I'm looking at GP zones. Then what happens? I'll have to call it nanostructure. So let us give a functional definition of microstructure very soon. And But then we note here an important slide. There are structure sensitive and structure insensitive properties, and structure sensitive properties even in bulk materials like yield stress and fracture toughness. If you want to look at a magnetic property, then the structure sensitive property would be the coercivity. The structure insensitive property would be the saturation magnetization. Okay. So those quantities you have to keep in mind. Okay. Now we have talked about a word called hybrids. So in bulk materials, you can have monolithic material like metals and alloys, ceramics and glasses and polymers. In hybrids, which is a superclass, you have composites, sandwich structures. Like typically you have one layer on the top and a certain layer in the middle and bottom layer. So for instance, the middle layer could be a foam so that the density of the overall of the sandwich structure is lower. There are structures known as lattice structures, that means they're made up of material and air. And we have already seen such an example of at least two examples of lattice structures. One is these hollow structures. That means it consists of oxygen in the middle and material outside, which is palladium. And we also seen this porous alumina, which is where it consists of pore and materials, and a very well organized set of pores, as you can see. Okay. It's shown from the top. These are deep pores. People actually grow nanowires using these as a template. So we have lattice structure. This should not be confused with crystallographic lattice. These are hybrids which are lattices. And finally, we have segmented structures. An additional important class of materials are called functionally graded materials. An old analogy of this kind of functionally graded materials would be your case carburized steel. That means the surface has a certain hardness and the hardness changes across the depth. Now, we are on one hand interested on the component, and we have phases and molecules on the other end of the spectrum, which is what we synthesize. The next scale, we have now introduced a term called microstructure, and multiple microstructures can come together to form materials or hybrids, and finally you have a component. So the component could be, for instance, a component made up of fiber reinforced material, like for instance the wing of an aircraft. Okay? Many of the aircraft components are nowadays made up of reinforced components, and they are all hybrids. Now let us take a formal look at what is a functional definition of a microstructure, because we will be, like we saw in the case of the alumina reinforced with carbon nanotubes, we need to understand this microstructure so that we can get the optimal properties. So the functional definition of microstructure can be given as phases and their distribution, defect structure and their distribution, and finally residual stress and their distributions. Why these distributions are important, we saw that in the case of the cementite, there is this in the steel, lot of cementite, the white structure is available in the matrix. This is not proving to be deleterious, but the little amount of cementite along the grain boundary is causing all the problem. Okay. So the distribution is a very important thing. And when I say distribution, I'm also worried about the shape of the structure which is distributing. So we have defined functionally what is called a microstructure, and often material scientists are called microstructure engineers who concern themselves with mechanisms. So there are two words, microstructure engineering and mechanisms. Please have a look at this slide, because this is an important slide, because the next scale after this is the component. And many of the things you engineer at the microstructure level, that means that suppose somebody asks you a question, what is the yield strength of 0.8% carbon steel? Just think about it in your mind. Meanwhile, I'll just give you a time for thinking that what is the yield strength of 0.8% carbon steel? So the answer to that question is that there is no such number I can give, because it depends on the microstructure. Is the microstructure martensite, tempered martensite, pearlite? That will determine the yield strength or the hardness. Okay. Now, let me skip this. The next thing which people have to keep in mind, which is important from the nanoscale perspective also, is that there are properties which change across length scales. That means when I'm worrying about a property, I cannot look at one length scale. Suppose I'm looking at yield stress, right? And I'm looking at the yield stress of steel, for instance, plain carbon steel. I will have to traverse multiple length scales, and I'm supposed not concerning myself only with the yield stress and say the fracture stress and the what you call the tensile behavior. Then I need to traverse across length scales. In this example, suppose I take a piece of copper. The piece of copper on the right hand side is isotropic, and this is a centimeter length scale. we look a little deeper into the microstructure, I would find grains, and within the grains, the crystal is actually elastically anisotropic. Okay, and but within the grain, you will find a lot of defects like dislocations, and between the grains, you have grain boundaries. So there is some amount of order and there is some amount of disorder. At the level of crystallographic unit cells, you would find that atoms look reasonably well ordered. But if you go to even smaller length scales, you will find atoms are actually vibrating and there is no order. That means what looks ordered, disordered at the very small length scale looks slightly ordered in the slightly larger length scale, again looks disordered in the slightly larger length scale, and so forth. That means that, and as you traverse across these length scales, the properties which emerge change, right? So that is an important thing which you need to cook. That means I cannot look at properties if I want to look at the underlying mechanisms, I have to underlying structures which are responsible for these mechanisms. Then I need to traverse across multiple length scales. Similarly, for instance, just to take an example of magnetism, um, if you look at this piece of iron, a piece of iron is supposed to be ferromagnetic, but then it doesn't stick. Two pieces of iron do not stick to each other. And that is because to reduce the magnetostatic energy, the material splits itself into domains. Now, if you look at the single domain, then from the far field, they all look well ordered. But between two domains, you can see the spins. Spins here refer to atomic magnetic moments. They actually change orientation, right? But there are magnons which tend to, that mean thermal disturbances which tend to disorder these spins. But what are the origin of these spins? At the lower level you go, you see that it's electron spin and electron orbital motion, which are essentially responsible for magnetic moments. But then you go to the next length scale, you find that often in the piece of iron, because of a strong orbital motion lattice coupling, the orbital contribution to magnetic moment is quenched. That means here again, I have to look across length scale. I have to go from the atomic level to the level of the sample. This example I'm skipping. Similarly, for a gear wheel, I also need to look at the design of the gear wheel to the surface, to the subsurface regions. Okay? And that means that I have to be able to not only make a component, but engineer its microstructure. Let me introduce you briefly to some of the terminology used in nanoscale materials. Typically, you can say it's 10 power minus 9, but that is not what you call usually a functional definition. And you can note that typically even materials which have 100 nanometers or more, or a few hundred nanometers, are often called nanoscale materials. But the interesting thing is that at what length scale do properties change significantly or interesting new properties arise? Okay, and they are not found in the bulk. That is when you should really think of nanoscale materials as being truly defined. Okay. An interesting problem is that you sometimes call something a nanomaterial. Okay. And sometimes you call bulk nanostructured materials or nanostructured materials. Obviously, the whole material is not nanostructured. A piece of copper is not nanostructures, but the grain size within it could be nanostructured. We just now saw the domain wall in a magnetic material. This domain wall could have a thickness of about a few nanometers or more, but the interesting, or 100 nanometers sometimes. But the important thing is that the material itself is bulk. So there are structures inside which could be nanoscale, while the whole material is bulk. These slides are there for completion. You may kindly go through this because I will share the slides later with the organizers. That you might have noted that nanoscience and nanotechnology have grown in the past, and they are very, very important because the nanoscience feeds the nanotechnology feeds the nanoscience. That means newer and newer instruments are available today because of nanoscience, and those instruments further help in developing newer aspects. Okay. So some of the things, for instance, you can think of a nanotechnology is a microchip inserted into the body, which can give you a controlled drug delivery or similar such examples. So as I told you, nano is applied to multiple things, and today you can talk about nano manipulation and nano manufacturing. And some of the techniques which have come to the fore are techniques like E-beam lithography and focused ion beam. Tools like high resolution lattice fringe imaging tools and atomic force and scanning probe microscopes have come to the fore. Nice example is a field emission gun can be used to fuse the ends of carbon nanotubes to particular DNAs, and then you can extract certain signals from this. And that means you can even characterize single DNA and perhaps even look at incipient stages of diseases. Okay. Nanoparticles are easy to understand. So I will briefly say, for instance, in this picture, I'm showing some silicon nanoparticles. But just because it's a nanoparticle, it does not give you any further information. Each nanoparticle itself could be polycrystalline, it could be amorphous as in this case, or it could be other kind of structures. So just because it's nanoparticle, do not assume that what is the internal structure of that. A nanocrystal is again easy to understand. I have shown you gold nanocrystals. On the right hand side is an HRTM picture where there is a nano precipitate. That means these are not freestanding nanocrystals, but they are nanocrystals in a matrix. One such combination is lead particles in aluminum matrix, which have been well studied in literature. These are four further examples of nanostructures. You can have nanoflowers, you can have nanospheres, quantum dots, micelle, nanocone, nanoflower, nanobrushes, etc., etc. So there are a huge number of array of these structures which come under the nanostructure category, and they have all been intensely investigated across the globe. Now, there is another phase which is used, which is important, is nano phase. What do you mean by nano phase? Okay. How do you define a phase? You can define phases based on the state, the atomic order, on the band structure, based on property. Like for instance, you can talk about a ferroelectric or a ferromagnetic property. You can even talk based on stability, like you can talk about a metastable phase or something. And here we also talk based on size and geometry of entity. That's where nanocrystalline phases come in. In this example here, this is a silicon nitride ceramic. There is a small layer of about 1 nanometer thickness, which is what is called glassy. And this is called an intergranular glassy film. And this is a nano phase. I mean, the grains themselves are bulk. They are in the microns range, hundreds of microns, but the phase in between the two grains is a nano phase. And why it has to be a nano phase is because it has a particular structure to it. It's not like the bulk glass found. It has got its own glassy structure. It controls its composition, etc. So this is a nano phase material. Traditionally also, for instance, if you look at precipitates, like in aluminum copper alloy, you can form GP zones and theta double prime precipitates, which also could be in the nano phase regime. This I already told you what are these nano composites, so I don't have to repeat this. Nano porous materials also I have told you already. And I've already told you that there are many nano related terms which are important. The first question you need to ask yourself, what is nano in nano? And this I alluded to you before, that sometimes you have a bulk material, but then there are only certain features in the bulk material which are the nanoscale, but then those features may then give you interesting properties to the material. So this is something you need to note. And so this is a very important thing. For instance, you may have a polycrystal in which the grains are nanoscale. So that is an important possibility. You can have freestanding diamond crystals, which are also in the nanoscale. There could be multiple examples, and we already seen pore size in a lattice structure, which could be in the nanoscale. And there are many of biological origin, like for instance, the DNA could be in the nanoscale. You can have virus, which are more prevalent today, as you all know. They could be in the nanoscale, etc. Okay. An important point to be noted is that sometimes that the structure itself may not be in the nanoscale, but the response could be as if it's in the nanoscale. One such example, though a rare example, is that if you drive alternating current through a thin conductor, now what happens is the skin depth could be of the order of nanometers, hundreds of nanometers. Suppose you have alternating current of the under a few hundreds of gigahertz, then you find that the skin depth can be thin and it can be of the order of tens of hundreds of nanometers. That means here the material is not in the nanoscale, but the response of the material is in the nanoscale. The reverse may also be true, that you may have a 100 nanometer glass particle, but its refractive index may look like that of the bulk. That means though you have a structure in the nanoscale, but it does not mean that the property is in the nanoscale. The property is as good as the bulk property. And we'll take up some more examples of such bulk properties later. That means the structure could be in the nanoscale, but the property is in the as if it's as good as bulk. So this we had seen briefly that you have an epitaxial device. Now in the epitaxial device, the film, for instance, is grown on a substrate, and the film could be in the nanoscale. And so therefore, the stress state is also in the nanoscale. That means the stress variation is could be very sharp and could be in the nanoscale. So that is, and this is important because now the strain in the film can be used to engineer the band gap. So what kind of a misfit strain you got between the substrate and the film can now be used to engineer the band gap. The opposite end of the spectrum are not nanoscale. These are called bulk materials. Typically, bulk materials are tangible materials. That means they have. Can somebody mute the? They are bulk materials. That means that they are tangible, and the properties consist that of the bulk. Now, I'll just skip this slide. So what are these bulk properties? All of you know that what is a bulk property. Now, nanomaterials are typically, if you look at even some of the 2000 ACTA material paper, they classified based on dimension. Okay. So sometimes you might hear of zero-dimensional nanoparticles or zero-dimensional nanomaterials or nanostructures, one dimension and two-dimensional ones. So what are these? How do you classify the nanostructure based on the dimension? And this is very, very important because, for instance, if you look at a carbon nanotube, it is like a one-dimensional nanostructure. That means you have one, what you might call a nanoscale dimension, and the remaining two are in the bulk. So that is what can be thought of as a one-dimensional nanomaterial. And along the length direction, it could be in the microns. But sometimes if you take a carbon nanotube and even reduce the length also to a few tens of nanometers, then you will observe very interesting properties, something known as ballistic transport. That means that in normal materials, because of impurity scattering and thermal scattering, there is some resistivity, right? Now in this carbon nanotube, there may be no resistivity and the electron can travel without getting scattered. And this is called ballistic transport across the carbon nanotube. So the dimensionality is a very important thing in this. A zero-dimensional nanocrystal, all the three dimensions are in the nanoscale, while in just now we saw an epitaxial layer. There are two, there is one dimension in the nanoscale, but there are two dimensions which are in the bulk. Therefore, I need to know, and therefore when I look at the properties, similarly what happened on a one dimension, suppose I'm talking about a one-dimensional nanostructure, along two of the dimensions, I'll observe properties which are different than the third dimension, which is of the longer length scale. Now, we use the word dimension, but we'll have to be a little careful what is meant by dimensionality of a nanosystem. When you take a thin beam, typically you consider, and you may have studied this in your strength of materials course, that cantilever beam, the length direction is thick, and the thin could be the transverse direction, right? And this is a thin beam. And there are interesting examples in nanoscale materials. Like for instance, suppose I grow nickel films on copper substrates, the example below. I would note that in this example, like I have nickel films on copper substrates, I would note that when the layers are very thin, and you can note here nickel is ferromagnetic while copper is not, then 7 monolayers, what happens up to 7 monolayers, all the spins are in plane. That means it behaves like a 2D ferromagnet. And when you increase, somebody help me with subtracting this.
Please. Kumar sir, please.
I think the because in my screen I don't see all the participants, so I can't mute from here. Maybe.
Yes, yes. Now you can continue.
So what happens is that then when you make it thicker, then the two-dimensional system starts to behave like a three-dimensional system. That means the spins, the magnetic moments, tend to cant out of plane, and therefore you can have a 2D to 3D transition, what you might call a dimensionality transition, which is very rare, right? So many of you might not have heard of dimensionality transitions in materials. So like we have Professor Anurag Gupta in mechanical engineering, works on thin membranes and studies defects in these membranes. And there are special kind of defects known as disclinations in these membranes. So he studies them. So you have a 2D to 3D transition. Now, some people will say that nano always existed. They're right. For instance, the F centers in stained glass or the GP zones or a DNA always were present. But there are new things which have come because of this emergence of nanoscale materials. And we'll have a look at them. These include the inverse Hall-Petch relation, the giant magnetoresistance, which we'll see towards the end of this seminar, super paramagnetism, super hydrophobicity, right? Wherein the contact angle can be greater than 165 degrees. Okay. And these giant magnetoresistance materials have been made to use as what is called spin valves. Okay. And there is also super surface activity. That means that though nanoscale materials have existed in the past, but this new emergence of the field has given us new phenomena like inverse Hall patch, giant magnetoresistance, super hydrophobicity, etc. And therefore, it forms a worthwhile area of activity. Now, what kind of technology can we do? We can do targeted drug delivery. We can do make super biofouling surfaces. We can make transparent ceramics. In targeted drug delivery, for instance, I showed you some hollow structures. So you can magnetically drive these hollow structures loaded with some sensors to a local region in the body wherein you can release them. Because one of the problems with drug delivery is that you normally oversaturate the body. You eat a pill, the whole body gets the whole drug, and it's while a small region in your body actually requires the drug. So you don't have to saturate your whole body. You can locally deliver it, and that too whenever the concentration falls below a certain level. You can have transparent ceramics. You can have rapid catalysis and also functionalization. So these are important things which can emerge in this new field. And people have actually made nanoporous membrane filters. They made sanitizing washing machines. You might have heard of this, I think Samsung Nano. I think they are making the sanitizing washing machine. You must have heard of non-wetting clothing. You might have biological sensors, scratch-resistant lenses, spin valves, and spintronics. So these are multiple applications which have come across. I'll just tell you what are briefly hierarchical structures. We talked about them. So this hierarchical construction is important along with a concept called self-assembly. And this is important because a single nanostructure itself cannot be amenable to an application. We need to make a structure which is much larger. And you can do though by taking a brick for example, and you can make a larger brick made of 4 of them. And
Kumar sir, please.
so we can make this hierarchical structure, starting with some basic building block. And this is like how our mason builds a wall, and then you can use multiple of these larger bricks to make even larger walls. So this hierarchical construction, along with a concept called self-assembly, is often used in by nature, first of all by nature, and second by, we have seen these bricks, right, these in the nacre, and also by engineers now to make these larger structures. I'll just show you 2 examples of these hierarchical structures which are very important. One is something like a lizard, which is called a gecko, in which the feet have got certain structures. They are called setae. Within this, you have a single seta, and within that, you have nanohairs. Now, this overall structure of multiple levels, that means you have nanohairs which are built into setae, which are again assembled into a certain array, gives you what is a unique combination of properties. That means now a lizard, for instance, can stick on the wall. And typically, a wall contains, for instance, some amount of distemper or a tuna, right? And if you make normally a very adhesive material, what will happen? All the surfaces will get stuck, and that's all. The adhesive property would have been gone. But here, these lizards' feet are such that they are self-cleaning, and that's the beautiful part of it. And not only is addition easily possible, but also de-addition. If you have some things which are very adhesive or difficult to debond, right? So this combination of properties is coming from this hierarchical structure, and this is found in the common lizard. Similarly, I also pointed out that you take a single layer of this. This is basically calcium carbonate, but this calcium carbonate is so brittle. But then this overall structure, which consists of these bricks and protein layers in between, and these protein layers further are built into a multi-layered structure like you can see here. Then this overall material, in spite of being mostly made up out of very brittle material, has got a very good toughness. And when I say toughness, I mean impact toughness. When I say impact toughness, I mean a good fracture toughness. Okay. So that's a beautiful part of this kind of an hierarchical construction. Okay. I just gave 2 examples, but you can think of more examples which are there. And one more we saw was the Lotus Leaf also. It's also a hierarchical structure. I pointed out this to you. If I just make a plain layer without these protrusions, then I would not have superhydrophobicity. But if I just make these protrusions, nano protrusions, or these micro protrusions without the nano hairs on top, then I would find that the superhydrophobic effect is gone. So therefore, this is a hierarchical structure which a Lotus Leaf uses to produce what you might call the superhydrophobic surface. And of course, how do you measure these? You use something called a contact angle measurement. And in fact, you will find that most of the leaves have what is called the dorsal surface, which are more superhydrophobic than the ventral surface. But in this case, it's the ventral surface. Now, we already answered this to a large extent, that why we need to go to the nanoscale. And we already seen that you can get important properties like super paramagnetism, for instance, but also that certain important combination of properties can only be obtained at this scale. And in some cases, which is very important to note, that when you go to the nanoscale, there is a drastic improvement in the properties. In the properties are constantly improving. For instance, the fracture toughness of nickel has been shown to increase from 100 MPa to 900 MPa when the nanometer grains are achieved. So that means that sometimes you have an improvement in the properties, but the drastic improvement only comes in the nanoscale. Okay. And we also want sometime the entity to be in the nanoscale, the functional entity, we already seen that. Therefore, we need to go to the nanoscale and make nanomaterials. Now, how does this property change come about? May involve multiple mechanisms. And as I told you that this is very important to know what mechanism is responsible. For instance, the most general case could be case A, where you have a change in size, that means reduction in size, which leads to a change in structure, which typically could be in crystal structure and the microstructure, which finally leads to a change in mechanism, and which finally leads to a change in properties. So there is a range of possibilities, and you need to work out for your individual case, like what is really happening to your material. Okay. I will leave this slide for a later study for now. Now, why do properties change in the nanoscale? One of the simplest reasons that properties change in the nanoscale is because there is less amount of material. Okay. And if you have less amount of material, for instance, you all know from school studies that there are atoms have discrete energy levels. While if you have take a metal, there are bands, that means energy bands. Now, why each one of those atomic energy levels is contributing to what you might call a quasi-continuum of these levels in the band, and therefore you have a band. Okay. But suppose I have a system, a nanoparticle with only a limited number of atoms, what will happen? My energy levels will get farther apart and will behave like a discrete level. Okay. And therefore, sometimes these are called exciton absorptions. Truly, they're not excitons in this true sense of the word, but they have discrete absorption levels. And this is coming from the fact, very simple fact, that you just don't have sufficient amount of material. So, and therefore the quantum size effects tend to dominate. So this is not a very profound or very difficult to understand aspect. The second important thing which you need to keep in mind is that dominance of surface and interface effects. Please keep this in mind, it's very important. Because, for instance, you were talking about creep in materials, right? Or you're talking about even yield strength of materials. If there is surface and interface or diffusion, for instance. Now, interface diffusion can dominate the whole process here in nanoscale materials. The proximity of surfaces means that there could be a segregation of second phase to the surface, right? Atoms could go and sit on the surface, right? So there are multiple things which are purely arising because of the fact that there is a large amount of surface or interface in these nanostructured materials, and much of the effects can come. For instance, normally in bulk materials, you will ignore what is called surface stress or surface tension. But in nanoscale materials, you may not be able to ignore surface tension. In nanoscale materials, again, for instance, you may have polar surfaces. Polar surfaces are surfaces with electrical dipoles. In principle, you could also have magnetic dipoles, and these can now dominate your properties. Surface plasmon resonance can become very important. So these are important effects which come because purely because the fact that you have proximity of surfaces and interfaces, and we will see some examples. And also the fact that you have proximity of the surface to most of the bulk. That means that if you take a very thin foil of gold, it will become transparent. Normally, because plasmon absorption takes place over a range of thicknesses, therefore gold becomes opaque. But you just don't have sufficient material here, and the material can transmit through it. Another important thing we'll have to keep in mind is the altered crystal structure and altered defect structure. We'll see examples later. For instance, suppose we will see that if you take a very thin crystal, it may become devoid of vacancies. Because copper, for instance, at room temperature, vacancies can be present in equilibrium concentration. They're thermodynamically stable vacancies, and these could go missing in the nanoscale materials. So therefore, you could have an altered defect structure. The other important thing you may want to note is that, for instance, is that one or more physical length scale, that means the geometrical length scale, may become comparable to one or more. That means a physical property related length scale could become comparable to the geometrical dimension. Very, very important. This is like we talked about ballistic transport in a carbon nanotube. That means the mean free path of the electron is already longer than the length of the nanotube. So there was no scattering event. Right. For instance, I also showed you a phenomena, just briefly mentioned a phenomena called giant magnetoresistance. How does this happen? This happens because the last example I've given here, for instance, the spin diffusion length. I'm not explaining in detail what is spin diffusion length here. The spin diffusion length becomes longer than the non-magnetic layer used in the hybrid, which is used to make up the giant magnetoresistance hybrid. So therefore, you have, this is an important points which you need to keep in mind. That means, number one, there's just lack of sufficient material so that you get some properties in the nanoscale. There is a dominance of surface and interface effects. There is a proximity of the surface to most of the bulk, right? And therefore, maintaining a composition gradient within the nanoscale is very difficult. There could be an altered defect structure. That means the defect in the nanoscale material could be very different from that in the bulk. And last but not the least is the fact that certain physical property of the physical length scale becomes comparable to the geometrical length scale, which can lead to some very interesting properties. Now, one thing sometimes is unavoidable is the fact that you cannot have an isolated nanoparticle because they will tend to sinter, they will tend to coagulate. And therefore, what you do, you put these nanoparticles, like for instance, you could take platinum and embed it in a titanium substrate, TiO2 substrate. You can see a TiO2 substrate here. And you may want to use this for a catalytic application. Now, this very fact that you embedded a platinum nanoparticle in a substrate can lead to an interface which can now enhance your catalytic property. So this interface was unavoidable because of the practical reasons, and that led to, for instance, a certain property which was enhanced. Sometimes new properties can also arise. For instance, you take bulk graphite. It is not ferromagnetic, but people study the defect states in highly oriented pyrolytic graphite, where the grain boundary states, or there is a report even of a gold phosphorus bond in a gold thiol coated gold. Because why do you coat thiol over gold is so that the gold particles do not sinter, and this can lead to states within it which have been reported to be ferromagnetic in some literature. So I don't know what's the final, is it true or not. So we have a range of reasons, and one of the reasons which is sometimes unavoidable is the fact that you're now embedding these nanoparticles in a substrate. Now, when you make a nanoparticle, the surface area increases. The first of these effects we saw, the increased surface area effect. And you can see here how you increase the number of particles. You can see that the surface area is increased. So this is some kind of a short tutorial. You can go through it in later. But the important thing is the surface area drastically can increase. And this is coming from the fact that you are increasing the surface area. Now, that means you take a small piece of a material and keep on breaking it up. That means you get a large number of particles from a small piece of material, and that can give you a large surface area. Now, you should not end up thinking that all is hunky-dory and all is fantastic with nanomaterials. There are a lot of problems. And until and when all these problems are solved, we cannot use them, these materials, in a widespread manner. And so some of these difficulties I'm highlighting here. The first one is difficulty in synthesis and isolation. That means sometimes you can make nanoparticles, but you cannot isolate them. They may coagulate, etc. These particles typically have a metastable state or a highly reactive state, and therefore they may get oxidized. They may react with other things in the environment, and therefore this is a serious issue. Impurities can easily be accommodated, as I pointed out, in the nanoscale, or either on the surface or in the bulk, and therefore this could be affecting your properties. Some of these could be nanoparticles and etc. could be harmful to the biological system, and therefore people working in such labs where they make nanoparticles, they should be a little careful about how they synthesize it. I didn't show you today a video. For instance, in our lab, for instance, there was we did some ball milling of a material, and when the person opened the ball mill, the whole thing caught fire. The whole chamber caught fire. Okay. So it becomes very reactive, and sometimes it can even catch fire in normal air. Recycling and safe disposal issues are not even being considered. Much research has to be done, and therefore these are issues which needs to be addressed. There are other challenges which need to be addressed, like consistency in quality, fast characterization techniques, scaling up of the production. Typically, I told you ball milling. Ball milling is a batch process, and therefore you typically don't produce in tons. For instance, people have used MOSI2 nano ball bearings. So, but then you can't easily produce these MOSI2 nanoparticles in large quantities. In Israel, some of the groups have produced them in reasonably good quantities, and therefore production in large scales is an important issue. Synthesis of hierarchical structures is just coming about. Sometimes it's only restricted to a few examples here and there, and so forth. Okay. Now let us take up some of the physics behind these nanoparticles and what we need to understand. You have a regime which you need to know is called clusters, and from clusters you can go to large clusters and nanoparticles, and then finally to the bulk. And this is the range of sizes, and you need to consider. And when you talk about clusters, for instance, there may be, as we shall see soon, that there are certain magic number of atoms which are stabilized. That means that for xenon, if you have n equal to 13, 19, 25, etc., and this is got a structural origin because they form what is called a Mackay double icosahedral clusters, and they are stable. In between numbers of atoms are not stable. There could also be stability in sodium clusters, which come from electronic origin. That means the entire thing made up of 8 sodium atoms or 20 sodium atoms behaves like a superatom. That means now it's like like you have electronic shells filled, they would give rise to stability. Here you have clusters of atoms, which gives rise to stability, and therefore they have an electronic origin, and this can be thought of as a superatom made up of a cluster. Now, these clusters, you have molecules, you have microclusters, small particles, and microcrystals. Okay, and many of these microclusters to small nanoparticles is a regime wherein interesting properties emerge, and we need to keep track of them. One of the nice examples of a nano crystal consists of gold, a 5-fold twin gold. Now, each one of these is a variant, and the total symmetry of these mimics that of a 5-fold crystal. But as you know, 5-fold cannot exist in crystals because it violates translational symmetry. Therefore, you can have small clusters in crystals having certain geometries which are typically not allowed in the bulk. That means that suppose I take a bulk of xenon. The bulk of xenon will not have a double icosahedral structure. For instance, in our own lab currently, we are studying certain nanocrystals of argon. Okay, argon is used because it's got a very nice, what you might call a Lennard-Jones potential kind of a behavior. Okay, it's a very nice material. There are inert materials, but we are not there. We use face-centered cubic as a cubic close pack structure or hexagonal close pack structure. Not these clusters. These happen in smaller sizes, and of course, this Mackay is Professor Alan Mackay, who used to be in the Birkbeck College, London, and he has visited Bangalore many times. So that's a very nice thing. So that's a very nice thing about this particular cluster. Very few people have actually solids named after them, like for instance, Plato, the Platonic solids, or the Bernal deltahedra. And Bernal also was from the Birkbeck College of London. And then also you must be obviously knowing our Fuller, right? The Buckminster Fullerene, right? So therefore, there are some clusters which are stabilized by certain magic numbers. So that's an important thing to know. And this is the size just below the size of the nanocrystals, right? So that's very important and very nice to know. I briefly mentioned to you about self-assembled ordered structures. I will just leave it here because it is maybe a little too taxing for today. Then there are other things known as core shell nanostructures. That means that you have an inside which is different from the outside. And these kind of structures have been sort of envisaged for drug delivery and other structures. In our lab, for instance, we have made palladium coated on silica. Okay, so there is palladium on the outside and silica inside. And sometimes we, of course, remove the silica from inside and we have a palladium hollow shell. And some of these core shell structures can develop interesting properties. Like in the case of cobalt, you can have cobalt on the inside and cobalt oxide on the outside. And they have something called an exchange anisotropy property as far as magnetism goes. There is one important thing which I am not emphasizing in today's lecture is the synthesis aspect. A whole volumes of material can exist on how do you synthesize these materials. There are a variety of techniques, and you may go through the literature to understand how these synthesis techniques exist and how we can get some of the properties which are based on these synthesis techniques. Next, let me talk about curvature effects and nanoparticles and what effect can it have, for instance, on the lattice parameter. Now, because of the fact that now you're not talking about a bulk material, you are going to be talking about the altered Gibbs free energy, which comes from the fact that these particles have a very curved surface, right? The radius of curvature is small. And this implies that their free energy diagram is not the one which you find typically for bulk materials. And such a material will tend to coarsen. That means they will tend to sinter first, then they will coarsen, etc. And therefore, you need to worry about this curvature effect, because below the curvature, highly curved surface, the concentration of vacancies may be altered. The concentration of other defects also may be altered. Now, what happens to the surface stress? Because now the atoms on the surface are less bonded, and therefore what happens? There is a higher surface stress, okay, or a surface tension in the case of liquids. Now this leads to an excess pressure, as shown by the Gauss-Laplace formula here on the left-hand side. Now what happens because of that? The surface tends to push on the material. In the case of bulk materials, you can just ignore it. You can say, okay, this is a very little of surface as surface to volume ratio is very small. But in nanomaterials or nanoparticles, you can't ignore this. And what therefore happens is that you can have a reduction in lattice parameter itself coming from surfaces. So you can see that you can get a lattice parameter reduction of about 1.5% when you decrease the size to about, say, less than about 10 nanometers. So this is an important effect which comes purely from the fact that you're in the nanoscale and surface stress is compressing the material. And this is in metallic materials, because in normal materials, what would happen in non-metallic materials, some of them which have polar surfaces, you could even have surface compression, which may lead to an increase in the lattice parameter rather than the decrease in the lattice parameter. So this is metallic materials. Of course, this is solid metallic materials. We have shown in the case of hollow metallic materials that you can even have a lattice parameter increase. The thermal expansion of metallic materials, as you know, when you heat a material, normally it expands. But they have found that in special cases like 4 nanometer gold nanoparticles, in a certain temperature regime below 125 Kelvin, the thermal expansion coefficient can change sign. That means that what happens is that you are heating the material, but the material is actually contracting. So this is a very rare effect and normally not found in the bulk counterparts. There are a few examples in the bulk counterparts. I think they are found in tungsten oxide, but most materials, you heat them, they expand. But in the special cases of in nanoscale materials, you may have even thermal contraction rather than thermal expansion. Now, next comes the melting point. This is another important thing which happens when you reduce the size of the particle. That when you reduce the size, you expect typically that the surface sometimes shows what is called a pre-melting phenomenon. Okay? That means it melts below the bulk. That's a pre-melting phenomenon. But when you reduce the particle size, and if you reduce the gold crystal, for instance, to 10 nanometer size, it melts 100 degrees below the bulk melting point. So that means the melting point is suppressed when you reduce the size. So you see that you're going to smaller and smaller size. That means the melting point decreases. This is very important even in practical experiments. For instance, we have heat treated thin films. And you would often find that if you cannot use the bulk melting point as your heat treatment temperature. We actually use the temperature and time which is lower for the thin films, the nanoscale films. So whatever reason, sometimes we are trying to cause precipitation, sometimes we are trying to cause nucleation, whatever may be the experiment you are doing. If you heat it to the bulk melting point, actually the whole film may vanish. So there is a depression in the melting point, which is coming essentially from the dominance of surface effects. Melting is a phase transition. There could be other kind of phase transitions you can study in nanocrystals. But the important thing you have to remember is now there is a very little amount of volume of material. So if you reduce a particle size to about 2 nanometers, as shown in the left-hand side, what could happen is that a single nucleation event itself could complete the phase transformation. This is very interesting, that you have a particle and the whole particle is of a size such that it is less than the critical radius for nucleation. And therefore, if I hope some of you might have read what is called the critical nucleation size. That means if you are undercooling a material, you're taking a melt of, say, copper, and you are below the melting point, then a small crystal has to form, which is of a sufficient size so that it can grow. Crystals smaller than that size would melt away and would not lead to any crystallization. So this critical size of a nucleus is called the critical nucleation size, and is given a symbol R star. So the nucleation event, which is called due to statistical random fluctuations, is uphill in Gibbs free energy, while the growth process is downhill in Gibbs free energy. Larger particles, if you take about 10 nanometer particles, and people have done extensive studies on cadmium selenide and cadmium sulfide on these kind of nucleation studies, you find that you may have a single nucleation event which leads to a phase transformation. That means you will always get a single crystal in the end for these two cases, the case of the 2 nanometer and 10 nanometer. Even larger particles, there could be multiple nucleation events, and you will obtain a polycrystalline product in the end. So even phase transformation behavior is changed, and it is not always necessary in the nanoparticles that the phase which forms first is what you would get in the bulk structure. Sometimes in nanoscale materials, the phase which forms could be of a different crystal structure than the one found in the bulk. Now, it could also happen that the critical nucleus size itself is altered in a nanoscale material, right? For instance, suppose I take a nanoscale thin film and try to cause nucleation. Then the R star, which I obtain, could be different. And for instance, in our nanoscale paper, which we published, we showed that the R star can be depressed significantly as compared to that of the bulk. That means the critical nucleation size itself could be reduced when you reduce the size. Further, these nano precipitates have stress fields around them, and nucleation events can happen around these stress fields, and that itself can also change the critical nucleation size. Okay, so these are important changes which happen as you go from bulk to the nanoscale. Now let us take a few examples of what is called the mechanical behavior and what happens to the defect structure in the presence of in nanocrystals. As I pointed out today in the beginning of the talk itself, I'll reiterate it for people who didn't join. In case you find me going too fast, yes, this is not a teaching class. This is extremely, extremely fast for somebody to learn. Whatever I'm teaching today in one or few slides, if I were teaching a course on this subject, like we have a course called MSc 694, which I often teach, which I sort of developed in IIT Kanpur. So that course, I would be taking 5 classes to teach one of the next slides I will be showing you. Okay. So that means that here in this, try to get the broader picture and the fascination and the possibilities, what you call an exposure. The details of these require hard study. Suppose I want to understand, as I pointed out at the beginning, you want to understand nanomagnetism. Obviously, you should understand magnetism first. Suppose I want electrical conductivity, I should understand normal bulk electrical conductivity first. Suppose I want to understand surface stress in nanomaterials, then I do understand surface stress in bulk materials. And I need to know Gibbs-Thompson effect, right? All those things here I need to understand before which I jump to the nanoscale materials. But that's not possible in a small lecture like this. But I hope I will be able to give you a broader spectrum exposure and tell you about the fascination of these materials. And therefore, some of you can go ahead and sort of enrich your research or your learning process in the future. The defect structure in nanostructures, nanoparticles, etc., could be altered with respect to their bulk. For instance, this is a paper by Professor J. Narayan, who was an alumni of IIT Kanpur, and he has also spoken in IIT Kanpur, a professor at North Carolina State University. He has shown that when you reduce the particle size of aluminum below 6 nanometer, then the system becomes vacancy free. And why are which vacancies are we talking about here? These are not structural vacancies. These are vacancies coming from thermodynamics. That means which are arise because of the minimization of Gibbs free energy. That means from the configurational entropy benefit, which is coming from the presence of these vacancies. Because presence of vacancies is going to break bonds, it is going to increase the Gibbs free energy, but the configurational entropy, which increases as seen according to the Boltzmann picture, gives you a certain benefit in the Gibbs free energy. So, but then system size is so small that the number of configuration state reduces, and therefore what you see that the system can become completely free of vacancies at a small critical size. This is very interesting. Copper also, it has been shown that below 86 nanometer, you can have vacancy-free crystal. Normally, a density, as I pointed out, is called a structure insensitive property. I don't worry about the density in a bulk material because of the presence of grain boundaries or dislocations. But in nanomaterials, I need to worry about it in nanostructured materials, because now, if you have grain boundaries or triple lines or quadruple junctions, right? So these are regions of defected regions where the crystal sees a break in the continuity. The periodicity is broken. Here, what do I see? I would note that the density of the locally is altered. That means the grain boundary has lower density because it has a lower coordination number as compared to the bulk. And therefore, when I go to smaller and smaller sizes, the volume fraction of these defects increases. That means I go to 10 nanometer, I find that the volume fraction of grain boundaries, triple lines, etc. increases. And this means that my relative density decreases purely because of the fact that I have a polycrystalline material. I would have completely ignored this if I were in the bulk. I would say density of the, say, micron size crystal, micron grain size crystal of 1 centimeter and 5 centimeters the same. I won't even worry about it. But here you see that when you go to 10 nanometer size, grain size, you note that the density has decreased purely arising from the natural contributions to a polycrystalline material. So this is very interesting. I will not talk about the elastic properties in detail, except to tell you that some of the nanostructures, like the carbon nanotube, is found to have very high elastic Young's modulus, right? So the Young's modulus can be very high. And what you can do, you can use these carbon nanotubes, therefore, to reinforce certain materials which are poorer in toughness, like alumina, etc. And you can make composites, and the modulus of a composite, depending on the volume fraction, will lie somewhere between what is called the iso stress limit and the iso strain limit. And people are accustomed to the terminology, might even call it the Royce averaging and the Voigt averaging to find the modulus of the composite. And you can increase the modulus of the composite. Like I had shown you before, that you can include carbon nanotubes in a nanocomposite with alumina. This has been done by my colleague, Professor Kantesh Balani. In fact, he's a co-author or co-presenter in the book on the NPTEL videos on nanomaterials and nanostructures. He works on biomaterials also, and many of those applications he's doing in his lab. And he has done some of the pictures I showed you on super hydrophobicity was the work he did when he was in Florida International University and later stages. In fact, he has done a modulus mapping of single nanohair of this Lotus Leaf. So this is from his group's work, where he has reinforced carbon nanotubes using an alumina and improved its strength. And you can find that the modulus of the alumina is now, which is originally about 350 GPa, can be increased to about 570 GPa, which is considerable improvement because of the presence of the small amount of carbon nanotubes. Now, the modulus of a polycrystal also decreases, like we saw the density. The modulus of the polycrystal also decreases because of the presence of these defects, which are the grain boundaries and other things. And therefore, normally you would have thought that elastic modulus or the Young's modulus, as in the case of an isotropic material, because Young's modulus and Poisson's ratio are used in the context of polycrystalline, what you call isotropic materials. And you know that truly speaking, given a cubic crystal is anisotropic with respect to fourth order tensor properties like elastic modulus. And therefore, what happens is that for now we make an approximation of isotropy, then you find that when you reduce the grain size, the elastic modulus or the Young's modulus can decrease. This is coming purely from natural effects, which we talked about before. Some of the early literature even talked about something known as supermodulus effect, But later on, it was seen perhaps this is an artifact of sample preparation. And this is something which all of you should note, that when you read literature, please make sure that how do you compare two data points? Many of the samples can be not naturally having the property, but it is coming from either contamination or the presence of residual porosity in the material, I mean, not fully sintered properties, or from some other effect which was uncontrolled, and therefore the property you see could be not truly reflecting of the nanomaterial. So we have to be a little careful in this aspect. When you reduce the size of nanoparticles or nanocrystals, what might happen below a certain critical size, the nanoparticles may become spontaneously dislocation free. Suppose I measure, take the strength of a yield strength of a nano whisker, which is free of dislocations. Then I would find that it yields of the order of gigapascals, right? And the stress you require to drive a dislocation is called the Pearls-Navarro stress, which is the shear stress at the slip plane level. Now you keep on reducing the size of the material, and a normal material, you know, has a lot of dislocations in it. And this dislocations helps you in doing plastic deformation, what is called the plastic deformation by slip. But when you go to smaller and smaller sizes, what happens is that these dislocations are attracted to the free surface by an effect called the image force. And when you go to nanoparticles, what would happen is that these dislocations can spontaneously move. You didn't apply any stress outside or any constraints. It spontaneously moved and left the surface. And this happens typically in the range of tens of nanometers. And you would have a dislocation-free crystal. And this happened because of the image force. This image force is a very interesting concept because a dislocation is not the extra, edge dislocation is not the extra half plane or the missing half plane. It is a nothing, a fictitious line between the two. The surface to which it's attracted is not the material, it's not the vacuum. It is a fictitious line between the two. And the way you calculate the force is making a fictitious dislocation of opposite sign in the vacuum, or the other side, you extend the material and put a dislocation opposite sign. Therefore, image force is a fictitious dislocation being attracted to a fictitious surface via a fictitious construction. But of course, the force itself is real, and this is called a configurational kind of force. It's not a point mass force, and this can lead to ultrasound crystals because all the dislocations left the crystal. So, the very interesting effect in the case of nanoparticles. Many years back, we calculated that these sizes happen to be in the range of 8 nanometers to about 36 nanometers. Okay. Now, SLB studied these dislocations in thin materials and found that thin crystals, if you put a screw dislocation in the center, it can twist. And this has been called the SLB twist. And one of the beautifully written papers, I don't have a reference here or not, was published sometime in the last 10 years, wherein it's called, the paper itself had a title called SLB twist. So similarly, an edge dislocation actually can cause a bending of a thin plate. And this is, of course, SLB I'm talking about is a famous J.D. SLB, who published a sequence of beautiful papers in 1950s and who is very well cited. And the collected works of SLB is written by Professor Anurag Gupta, who is a professor in mechanical engineering in IIT Kanpur. Okay, so he has written the book on collected works of SLB. So these plates can bend because of dislocation, which does not happen in bulk. And we have shown that, and in such materials, dislocation, thin plates, the dislocations can become mechanically stable. They don't become thermodynamically stable, they become mechanically stable. And the fact that screw dislocations can be mechanically stable in a thin cylinder was shown as early as 1950s by J.D. SLB. The edge dislocation part had remained unsolved, and we showed it in about, I don't know, about in the last 10 years sometime, that it also can be mechanically stable. Interesting effects can arise in such thin plates with dislocation. You can get something called a zero stiffness regime. Okay. I'm just skipping it. I'm just telling you such interesting effects arise. I will be glad later to tell you how these effects arise. And you can have something called as reversible plastic deformation due to elasticity in such kind of structures. One of the things which you are not to ask is that how do I test such nanostructures and nanomaterials? It's a very challenging thing. So because when you test a nanomaterial, you may have to use a substrate. You may have to use a material where you did not know the porosity content which contaminated your result. Of course, the author of this I was referring to before is the ACTA material paper is Herbert Bleeter. used the dimensionality to classify in his 2000 ACTA material, special volume and nanomaterials. Okay. Professor Herbert Glater has institutes named after him even in China. They're called Herbert Glater Institutes of Nanoscience and Nanotechnology. Incidentally, he has also visited IIT Kanpur and also our lab in IIT Kanpur. So you have series of problems like the small amount of entity you've got, artifacts introduced by processing rules, measurement uncertainties, etc., which you need to address if you're really wanting to characterize these materials. Some techniques people have used to produce bulk quantities of nanostructured materials like equichannel angular pressing, accumulative roll bonding, which you have used in our own lab to produce submicron scale materials. People have used, for instance, corrugative forming. One of my doctoral scholars is going to, I'm co-guide of that student who is going to defend his thesis next week, who has worked on this multi-pass corrugated forming. So there are techniques wherein you can use, which are called severe plastic deformation techniques, which can give you bulk quantities of these materials. Let's talk a little bit about the grain boundaries in these materials. And just that I want to tell you that there are special grain boundaries, and these grain boundaries can have profound effects. The structure of these grain boundaries could be same as the bulk or could be different from the bulk. So there are important results from Surya Narayana's group, who was a professor in BHU originally. This is my guide, PhD guide, Professor Ranganathan. And so Divakar is currently at IGCAR. So they have all shown a variety of results. They are very interesting. There have been cases where there are these nanostructured grain boundaries. There have been, I'll briefly tell you that in nanostructured materials, people thought that there are very special things going to come because you're going to reduce the size and you're going to have, extremely high creep rate, superplasticity, etc., etc. Some cases this has been found to be true, and some cases this has not been found to be true. So what did people expect? That one of the things they found was the Hall-Petch relation. That means when you reduce the grain size, you expect strength to increase, but you keep on reducing the size. It can't be that it can go on forever. That means that people have found that at certain grain sizes, like which is of the order of about 25 nanometer odd, you find that the Hall-Petch relation starts to break down. And in special cases, there has even been what is called the inverse Hall-Petch relation. That means you reduce the size, but the strength, instead of increasing, actually decreases. So this is called the inverse Hall-Petch relation. There are materials in which a higher creep rate or creep rate at a higher temperature has been found. Why do you expect a higher creep rate? Because now the diffusion lengths are smaller, right? Because you have a nanostructured material. The grain boundary diffusion is going to play a very important role. And you can also have grain boundaries sliding. One of the important mechanisms of creep is grain boundary sliding, which also you would expect to occur. In some materials, this has been found to be true that creep occurs at higher temperatures or superplasticity occurs at higher temperatures, but this is not universally true. Okay. So this is something which you need to note, that some cases you do find some interesting properties coming up, but some cases it has not been true. Okay. So I also talked about the inverse Hall-Petch relation. One of the nice books in this area is written by Professor Ramesh, who is at Johns Hopkins University. And one of his doctoral scholars worked in his lab was Professor John Lagadda, who is now currently at IIT Bombay, who does testing of these nanoscale samples or submicron scale samples in situ, inside a scanning electron microscope. So in his book, you would find a lot of these interesting examples of where do you find inverse Hall-Petch relation extra. His whole book is on nanomechanics. People have produced these nano-laminate structures like the titanium nitrate, niobium nitrate, wherein they have obtained a very high hardness value, about 50 GPa, while the single layer hardness is only about 20 GPa. So, and also they found that you have some kind of a Hall-Petch kind of behavior with the thickness of the layer vis-a-vis, not the grain size now, because Hall-Petch relationship was originally developed for the grain size, thickness of the layer vis-a-vis the hardness in this case. Sometimes you can also plot this tensile strength. So people have even produced nano-twinned structures, and they have found that some of these nano-twin structures, and I remember this was a paper in Nano Letters, where these nano-twin structures can give rise to strengths which is higher than the shear strength of the material. That means the theoretical shear strength can be exceeded in such kind of nano-twin materials. So let me flip a few slides here. because I just want to show you that apart from mechanical behavior, there are few important case studies which are nice. One is the case of, this is a paper in Physical Revelators and published in 2008, in which they used a carbon onion in which they had a gold nanocrystal. They punched a hole using an electron beam and did a nano extrusion experiment. Okay. So this was under some kind of a compressive stress, and they did a nano extrusion experiment of gold. And they found that they called it the ultra strong regime, in which these gold nanocrystals stood a stress of about 20 GPa. Okay. And the interesting thing is that you use carbon onions. Professor Ajayan, who happens to be a professor associated with the IIT Kanpur's new department, which you might have known I'm associated with, the Sustainable Energy Engineering Department, professor at Rice University, originally at Rensselaer Polytechnic Institute. When he was in the same group I was in, which is Max Planck Stuttgart, he used his carbon onions to entrap carbon inside and turn it into gold diamond. So what happened? This carbon onion produces so much pressure that under the electron beam, and there in Stuttgart we have a 1.25 million volt transmission electron microscope, and this produced diamond inside, and that was a paper I think published in Nature. So this is a much later paper than that. People have even tried to deform nano silicon single crystals, and they found something called a pop-in effect, which is not found in the bulk counterpart. And people who are accustomed to these are called nano indentation experiments. And this happened because of the fact that you're now nucleating dislocations in silicon, which was devoid of the. The last topic I will deal with is called magnetism in nanomaterials. And as I told you before, to understand magnetism in nanomaterials, you will have to obviously understand magnetism per se, right? And that's and not everybody works on magnetism, right? So kindly bear with me. All I want to do here is tell you that we use a word called nano clusters, right? We even saw there are magic clusters which are stabilized, right? We even talked about dimensionality transition. We told that domain walls are by themselves nanostructures. So, but magnetism is a benchmark. That means if I study magnetism, I can get all the interesting things which we have been talking so far coming out nicely in one single property called magnetism. So what happens if I have nickel and I have bulk nickel as about 0.56 Bohr magnetons per atom? If I reduce the dimensionality, I see that the magnetic moment per atom can increase, right? Why should it increase? This 5.6 is the wrong number. Sorry, this is the correct number. I can show you later. It's some 5.4 or something. So why this increases is that, as I pointed out to you, the orbital motion magnetic moment is quenched in bulk iron or bulk nickel for that matter. When you make nanomaterials, this partially gets unquenched, and therefore you have an increase in the magnetic moment. Now, if the amount of material is less, what happens? The thermal disordering takes over, and therefore you would, at certain small particle size, and as a thumb rule you can remember, when you reduce the particle size, it's as good as increasing the temperature. And what happens when you increase the temperature in a ferromagnetic material? It becomes paramagnetic, right? That's what it happens. So here you're reducing the size to produce a paramagnetic material, and such a material is called super paramagnetic. And if anybody has known from school days that you can draw something called a magnetization magnetic field, you have something called a hysteresis loop when you produce for iron. But for super paramagnetic iron, the hysteresis loop vanishes, and therefore the coercivity goes to zero. It's a very interesting thing that by reducing the size, which is equivalent to increasing the temperature, you're producing a super paramagnetic material. Now, people have produced clusters of atoms, and they have produced clusters of iron atoms, and you find that the magnetic moment oscillates wildly in these small clusters. You may have, say, for instance, 12 atoms, you may have a magnetic moment which is very large, and 13 atoms, the icosahedral cluster, suddenly the magnetic moment, 12 atoms, it will suddenly fall down. The iron is the bulk limit, 2.19. It's about 2.2 Bohr magnetons. Why does iron have such an irrational or a very strange non-integral number of magnetic moments? That depends on the band structure and the way the upspin and downspin bands are filled. But the important thing is that just add one atom and the magnetic moment changes so drastically in the small cluster regime. In the large cluster regime, now you can see that you can demarcate the small clusters and large clusters using magnetic moments. You see that the variation becomes smoother. But then it's still oscillating, and finally it slowly approaches that of. And that means that now I can produce a higher amount of magnetic moment, make it oscillate in the case of nanoparticles or nano. And if you look at this curve carefully, you would find that when you reduce the particle size, certainly some point of time you will have a single domain structure. And this single domain structure will have the largest coercivity. That means the entire particle is a single domain, unlike a bulk. So not only could you get a single domain structure, and single domain structure means you're paying price now in terms of the magnetostatic, and each one of those particles is now like a nanomagnet. Unlike a bulk piece of iron. A bulk piece of iron is not a magnet. It's in fact non-magnetic, right? It doesn't stick. It's ferromagnetic, but it's non-Chumbakీయ. So you can have super paramagnetism and single domain structures. And you can enhance the magnetic moment per atom. But more interesting is the case of chromium, which is antiferromagnetic in its normal nature. But when you reduce the particle size, you can get ferromagnetic chromium, a material which is antiferromagnetic. And by the way, antiferromagnetism in oxides like manganese oxide is much easier to understand, which comes because of something called a super exchange, than to understand it in antiferromagnetism in these metals, which look simpler, but they're very difficult to understand. Chromium and manganese are two antiferromagnetic metals, but then they are behaving like ferromagnets because of the small size. The last topic I will talk about today is something known as giant magnetoresistance, because this is a very important effect. The discovery of this led to the Nobel Prize. Okay, so here what happens? You have a ferromagnetic layer like iron, which itself is in the nanoscale regime, 30 angstroms. You put a small chromium layer, which is called like a spacer layer, which has got about 9, what you might call 9 angstroms. Okay, so I was just checking the chat box just in case our Manish is scolding me or something on the chat box that I'm exceeding my time. But this is the last slide. I will stop with this. So you have this non-magnetic layer, and you could in fact replace it with a non-conducting layer also. But here it is chromium. Okay, and chromium is non-ferromagnetic. Now, what does this chromium do? It does multiple roles. It separates out these two ferromagnetic layers, and the separation is such that in the natural state, which is in the absence of any external magnetic field, the magnetization in the top and bottom layers are oppositely oriented. That means in the top layer, you would have a magnetic moment which is, say, to the right. In the bottom layer, you would have magnetization to the left. Okay, so these are magnetized in opposite. And this kind of, why they are oppositely oriented? This comes from something called similar to something called an RKKY coupling. In NBS read a solid state physics book, the K, one of the K stands for Kittel, the famous author of the solid state physics textbook. And therefore they are anti-ferromagnetically coupled. Each one of those layers itself is ferromagnetic, but they're anti-ferromagnetically coupled. And this chromium layer is giving that spacing so that it can become anti-ferromagnetic. You bring them closer than about 5 angstrom, they'll get ferromagnetically coupled. The spins will be on the same direction. The second distinct role that this chromium does is that it is smaller than something called as a spin diffusion rate. So now what happens when current starts flowing through the magnetic layer, it becomes spin polarized. That means now the magnetic moment of individual electrons is all pointing in the right direction when it's in the top layer. When it goes into the bottom layer, what happens? It slowly starts to lose its spin memory. But then because it's smaller than the spin diffusion length, it retains most of its memory. But when it enters the second layer of iron, all the magnetic moments of the atoms are located in one direction. And in iron, the preferred direction is the 001 direction. There is a strong scattering of these, but this scattering is coming not from thermal scattering, not from impurity scattering. It is coming from spin-related scattering. It's spin-driven electron scattering. And this leads to a high resistance state. When you apply an external magnetic field, both the magnetizations have become in the same direction as in the below. So what you're doing is switching the bottom layer to the right, and this becomes a low scattering regime, or the state in which there is lower resistance. Now you can switch between these two states, as I pointed out, just by applying a magnetic field. So you have something called a magnetic resistance, which is coming from spin-dependent scattering, and you can switch between these two states, which can be used to create spin valves, etc. And this is the phenomena of what is called the giant magnetoresistance. And this is coming from a hybrid, number one. It is coming from nanoscale effects, number two. That means if I make the chromium thicker, it's not going to happen. Okay. And it's coming from a very important thing that now the spin diffusion length, which is a physical property, is comparable to the nanoscale dimension. In fact, the nanoscale dimension is smaller than the spin diffusion length. So you have all your physics coming through in one shot, that you have a single domain structure, which again comes in the nanoscale. You have to be above the thermal disordering temperature. Either you have to operate the device at low enough temperature. Otherwise, as I pointed out, if you are below, if this 30 angstrom happens to be below the what you call the super paramagnetic transition, then again you have a lot of physics coming to in one single shot. And you can make a device out of these things. These are memories which people are making out of these giant magnetoresistance materials. Related phenomena like tunnel magnetoresistance, etc., also have been investigated. So I thank all of you for what you might call, I showed you nano explosion, right, some time back. So this was, I presume, some kind of an explosion at a very high strain rate loading, which happens in impact loading. Sorry for that. And as I told you, I hope I have been able to give you some kind of an exposure. And 2 o'clock lectures, I don't know, I would have fallen asleep. I hope some of you at least, because of the bang, not because of my good talk, but because of the bang of the nano explosion, stayed awake to listen to you and listen some part of it. I'm indeed sorry for going so fast. As I told you, this is a complete course. Even part of it is a complete course. Even I want to talk about giant magnetoresistance, I will have to take 2-3 lectures to introduce it. But thank you very much once again, and I thank the organizers also. Now I'll take any questions. Let me get
Thank you, Mr. Anand. That was an excellent presentation. You have packed enough for an entire course. I think that's a lot of information in 1.5 hours. So I'm sure the participants are eager to go at you for questions. For starters, you can look at the chat box, and maybe as in a first come first service, if you can scroll back and start answering the questions, it would be nice.
Amit Bhattacharya's question, which is very simple for me to answer, because
yes,
I really don't know the answer, because he's talking about permittivity of DNAs and things like that. Sorry, way beyond my understanding what is the permittivity of DNA. So I can't answer that question. So I really don't know. I've not worked on any such materials. The next question is how inverse Hall-Petch relation happens. Okay, that's the next question perhaps. So what is happening is, what is the reason for the Hall-Petch effect? Some of the important experts have, normally people say it is the dislocation pileup at the grain boundary which leads to the Hall-Petch relation. But people are repeatedly now thinking that that is not true. I've talked to experts like, for instance, Professor Mahajan, originally who used to be at the Carnegie Mellon University, and who has written the, what do you call it, very tough book, tough volume to write on what is called the deformation twinning, one of the proceeding, but difficult book, volume to read. So now they believe that the dislocation pileup mechanism may not be a good enough explanation for the Hall-Petch effect. Whatever it is, it's an experimental observation. Now, when you keep on reducing the size, at some point, some size you would expect that the strength would be so much that it will go above the theoretical shear strength. So what is the theoretical shear strength? Where the material can just shear, the whole atomic plane can shear over the other. So obviously, the Hall-Petch relation is going to break down at some stage. Now, but people have found that in some materials that there is, and when you go to smaller and smaller sizes, I also told you there is another effect, that you may have something known as the image force coming from free surfaces. You may have dislocation sinks acting at grain boundaries, etc. So some of the early reports of inverse Hall-Petch is still questionable, but people have found in some materials that it's reasonably reliable, and it is coming basically from the fact that the Hall-Petch, whatever the tenets of Hall-Petch are broken down, and therefore you don't expect it to be true any further. That's so as simple as that. Next question is even more interesting. I perhaps don't have an answer. This is from Dr. Mirzana. Is inverse, the previous question was from Dr. Rajshekharan, I think. The next one is from Dr. Mirzana. He's asking, is inverse Hall-Petch equation applicable only to nanomaterials or having an effect on functionally graded materials also? Sorry, I have not read the latest literature on this. Functionally graded materials, I presume it might happen, but I showed you in the case of the nano layers, right? Nano sandwich layers. There, apparently the highest strength comes when you have one dislocation in each layer. And I'm sure even in these nano layers, these multi-layer structures of inverse Hall-Petch relation is going to break down. But sorry, I've not read the latest literature on these functionally graded materials in what you call in the development with regard to Hall-Petch. Though my very first postdoc, I worked actually on functionally graded materials. So, but I have no idea what is in the case of nanoscale materials.
Yeah, I mean, there are no more questions in the chat box, but I'm sure there will be somebody asking you, wanting to ask you questions orally. Please go ahead. Anybody wants to ask any questions orally?
Hello, sir. Audible, sir? Hello.
Yes, yes, audible.
Okay, sir. Thank you. So, sir, when you're discussing about the time of 0D to 3D, my question is related to that. When you convert a 0D to 1D by, take example, ALD process. So when you example, two things I will be say clearly. One is 0D by example, and one is 0D to 1D by synthesis. So my question is that when we see the nano property and nano crystal property in 0D, and when convert 0D to 1D, so the property will be same, yeah, it will be changed.
Okay, so
again,
sorry,
if I go,
sorry that your audio was not completely clear. I perhaps mentioned somewhere in my lecture that first of all, I need to know the property. Which specific property are we talking about? Without talking about a specific property, as I pointed out, for example, the refractive index of glass nanoparticle may become bulk like even by 15 nanometers, right? People have found in 90 nanometer crystals, the thermodynamics of bulk start to operate as far as vacancies go. That means vacancies are stable. Now, so therefore, what property are we talking about is very, very important, number one. Now, the dimensionality which we talked about, for instance, if I have, just because one dimension is longer than the other, I may not want to call it a 1D nanoparticle. Yes, geometrically you can call it, but there may be no difference between the three dimensions. So as far as the property goes, it may not be one dimensional or zero dimensional. But sorry that I missed the initial part where the voice was not clear. What exactly is your question?
So actually, take example that I want to make a atomic layer deposition of nanoparticle. Take example of gold. So when I choose only one gold nanoparticle and I take several gold nanoparticle and make 1D. So when one nanoparticle is 0D and several nanoparticle make a thin layer, take example of 1D. Yeah. So my question is that the property have what had 0D nanoparticle will be same have the thin film of several gold particle in a layer.
Okay. Before I go to a layer, let me cite a very nice work which was done by Professor Ravi Shankar of IIT Bangalore, next to Ramaya, who happened to, I knew him from my school days. We prepared together in school days, I know him. He's currently a faculty in the Material Research Center of IIT Bangalore, and for instance, Guru Rajan, who is in IIT Bombay. Okay. In fact, if I rotate my camera, I can show you some drawings drawn by Guru Rajan's daughter. Okay. I have some paintings in my room, drawing and paintings, which framed kept here in my office, which were drawn by Guru Rajan's daughter. So they have done a beautiful work in which they had drawn one-dimensional nanoparticle, nano wires. And these one-dimensional nanowires were produced by starting with nanoparticles. And then they had used micelles, etc. So they had gone one dimension, and then they then grow a nano layer. And they showed that the atomic layers within these are buckled. So it's a very nice paper. I don't remember. I think it was in Nano Letters or ACS Nano, one of those journals it was published. So they have shown that the atomic layers are buckled in the case of the nanowire. That means which were originally straight, I presume, in the nanoparticle, have now got altered in the case of the nanowire. Okay. Now, in the case of a 2D structure, which means you form a nanofilm of gold, what is the property you're looking at? By the way, sorry, I missed that.
I can say electric property.
Electrical property, okay. So now, in the wire, there were two dimensions, which obviously the density of states, etc., is going to be different. So nanoparticle is going to have a different density of states. The wire is going to have a different density of states. You plot them. The film is going to have a different density of states. The plasmonic absorption is going to be different, right? Like, so each one of those properties obviously is going to have a certain characteristics, which is now dependent on the geometry. Is that all the answer you wanted or something you wanted?
Yeah, yeah. Why I ask questions, sir? Because when people are doing research, if they want some good result, they are going to different dimensions. But my question is that if you want a good result, why not to take a same particle and change the dimension by azimuthal atomic layer deposition or CVD? So by changing the materials, why not take one material and get a different property? That's based on this question, I asked this question.
Why can't I take one material, change the dimension, and get different properties?
Yeah.
Good question. Very good question. I guess the answer might be the fact that not every kind of property can just be tailored by dimension. So some properties may change very sensitively, but some of the other properties may not be obtainable at all by just changing the dimension, right? Like we saw just now, to just give one effect we just now saw called super paramagnetism. That can be, or tailoring the Curie temperature. That can be done by changing the thickness, dimension, etc. But if I want an effect like giant magnetism, clearly not possible by changing only the dimension. I need hybrid. I need hybrid with certain, each layer having certain properties, certain Curie temperature, every single thing I need to know. So I presume that the reason is that the kind of properties which are tailorable purely by dimensions are limited.
So the next is, when you discuss about all your session, you discuss about the physics behind the nanoparticle. So my question is that, what's the chemistry behind the nanoparticles or nanorod or any dimension? Till now we not discuss. Chemistry means you say bonding, you can say reaction. Till now we not discuss at nano level of any particles.
Okay, sorry that I did not discuss that in today. So when you're doing a synthesis, sorry, I'm not going to again answer it in any kind of detail now, that any kind of synthesis process, you have to know your chemistry, right? And as far as the remaining of the thing goes, I don't differentiate between physics and chemistry. They are the same basically. But as far as synthesis goes, often a lot of chemistry is involved. I might have even shown some of the results from my own group where we use some hydrothermal synthesis, or we sometimes use flame synthesis. So the chemistry is rich there, and the chemistry is going to determine the amount of impurity level, etc. So clearly, you're right. The bonding is going to be affected. Every one of those things are important, no doubt about that.
Because whenever doing anything, whenever synthesis anything, we are doing with chemistry only.
Absolutely.
The things you are seeing by characterization by physics. So we start with chemistry only and reading on physics. Yeah. That's why I asked that question.
Very true. Very true. Sorry, I completely missed that. And even when I teach a course, I don't teach much of those synthesis methods. Though in a lab, when we have to do research, we have to synthesize. So I said only we use sometimes arc discharge, sometimes we use flame synthesis, sometimes we use hydrothermal synthesis, sometimes we use ball milling, we sometimes use accumulative roll bonding. They are all across the gamut.
The next is, when we discuss about 2D, nowadays so much 2D material came like MXCNE, TIU to 2D materials. So when we discuss 2D material, we are taking only one plane. So when you take 2D material of MXCNE, there is a different layer which has some gap between any layer. So can you say it is a 2D materials?
Okay, I think this is a very general question. I presume there may be bigger experts than me to answer that very question. When people say 2D, again, the same classification goes. That means there are two dimensions which are larger. And often there are layers like graphene, and there is a weak bonding, and there are graphite, or there are layered structures. And so that's what they call 2D materials, I presume, in general. So I am not sure what exactly is the question. I presume you yourself know the answer better than me, I think. So there is a layer in which there are certain properties in the layer, and there are out of layer properties. And when you say 2D, typically people don't exactly mean one graphene layer. Sometimes they could mean a multi-layer graphene, or they also call that as 2D materials, or multi-layers of MXCNE, as you pointed out.
Okay, thank you, sir. So in the slide, we discuss about the one specific criteria to find that 1D dimension, that is L by A should be greater than 20. Length by area should be greater than 20, you mentioned for 1D. So for 2D or 3D, you can mention anything else?
Yeah, you can work out, I presume. What we said is that suppose in mechanics, like for instance, suppose you use the thin beam theory, right? Or the shell theory, right? Or you evolve some criteria, right? That the thickness should be much smaller, L by D ratio should be so that you can call it as a beam, or and therefore the analysis can be simplified. So it's just that those kind of things which you can refer to in a simple mechanics book. So you can evolve such criteria. That means one of the dimensions is much smaller than the other two. Then you can treat it like a membrane or a 2D shell, right? Or a thin shell, for instance. Like suppose you are developing elastic properties of shells, then you will use thin shell only when it's of a certain thickness compared to the diameter.
Okay, thank you, Mr. Dhananjay. Dr. Subramanian, there was just one clarification. You were talking about magnetism of hybrids, and you said somewhere that this led to a Nobel Prize. Can you throw some light on it?
I think it's the Grunbaum's group, right? I can Google it. I mean, it's faster for me to Google and let you know. It's what's that? It's since it is Wikipedia will give you all the work.
No. Was it in relation to whatever you are talking? You said it led to a Nobel Prize. I was just wondering what it was.
So the discovery of the giant magnetosis was a Nobel Prize work.
Okay.
This particular, why did it go to Scholarpedia? But did not go to Wikipedia. Okay, let me check Wikipedia. So this was won by Albert Fert and Peter Grunberg in
Nice.
2007. Okay. This was the giant magnetosis work.
All right. So if there are no more questions, I think we should thank Dr. Subramanian for his time and for his scintillating presentation. And that was a lot of good information. I hope the participants have learned quite a lot today. And so on behalf of the institution, Atal, training and participants and ourselves, thank you once again very much. Have a good evening.
And you nicely pointed out that a lot of information. So there is, as you see, there is information, knowledge, and wisdom.
Okay.
So this was the lowest level. It is definitely information only. I hope if you can, all of you can spend in the particular area you are really interested. Suppose you're interested,
Those who can
someday you can transcend this low-level knowledge, information to knowledge.
No, that I think should be left to the individuals. If they can cull out something out of the information, then it becomes wisdom and whatever that you were just telling. I think it depends on us individuals to take it out and put it to the right use. Then it becomes wisdom.
Thank you very much, sir.
Thank you, sir. Thank you once again. Thank you all the participants also.